In 1949, the Soviet Union detonated its first atomic bomb. Within months, two 4-bombers, reverse-engineered copies of the American B-29, could cross the Arctic and reach every major North American city. Radar stations could detect them. But detection and response are not the same thing. Warning time was 6 minutes at best. The aircraft tasked with stopping them were piston-engine night fighters from the Second World War. Too slow, too blind without clear skies, too few to cover a continent. If bombers got through, cities ceased to exist. Gone. Both superpowers understood this arithmetic. Both built their defense doctrines around one scenario: bombers inbound, warheads armed, clock running. The question was never whether someone would build a machine fast enough. It was whether they could build it before the math ran out. And that desperation produced the most extreme aircraft ever conceived. The first answer carried nuclear weapons of its own. The Northrop F89 Scorpion entered service in 1950 as the first purpose-built jet interceptor in the United States Air Force. Twin Allison J 35 turbojets, an AN/APG-40 radar coupled to a fire control computer, primitive by any standard that followed, but nothing like it had existed before. Early variants carried salvos of 2.75-inch Mighty Mouse unguided rockets designed not for precision, but for saturation. The idea was simple: put enough explosives into the sky around a bomber formation and something would connect. But the Scorpion's most disturbing chapter was the J model. It carried the AIR-2 Genie, an unguided nuclear air-to-air rocket fitted with a 1.5 kiloton warhead. Accuracy was irrelevant when the blast radius solved the problem instead. 36 active squadrons and 17 Air National Guard units flew the F-89 across North America. It also killed its own pilots at a staggering rate: 383 accidents per 100,000 flight hours. Subsonic, structurally fragile, and armed with atomic weapons, launched into the sky over American and Canadian territory. This was the baseline. This was where it started, and already the calculus was shifting. Soviet bomber designs were getting faster, flying higher, pushing further. The interceptors had to outrun them, or the entire framework collapsed. Something faster was already on the drawing board. It nearly failed before it ever flew. The Convair F-102 Delta Dagger was supposed to be the definitive leap: supersonic speed, a swept delta wing, a radar-guided AIM-4, Falcon missiles housed inside an internal weapons bay, no guns, no rocket salvos sprayed across the sky. This was precision killing, engineered, calculated, clinical. But the first prototypes could not break Mach 1. The delta wing generated so much transonic drag that the aircraft was slower than the subsonic jets it was designed to replace. The entire program nearly collapsed under that single failure. What saved it was a breakthrough from NACA engineer Richard Whitcomb, the Area Rule redesign. By pinching the fuselage where the wings met the body, Whitcomb's solution reduced drag enough to unlock supersonic flight. 1,000 F-102s were built. They became the backbone of American air defense through the late 1950s. On carrying radar homing and infrared Falcon missiles against simulated Soviet Tu-95 raids in exercises that stretched across the continent. But the Delta Dagger exposed a critical flaw buried inside its own doctrine. The AIM-4 Falcon was unreliable in anything resembling a dynamic engagement. Targets that maneuvered, changed altitude, or flew unpredictably defeated the missile with disturbing regularity. When F-102s were later sent to Vietnam, a war no interceptor was built for, those limitations proved brutal and unforgiving. Still, the F-102 validated something no aircraft had before. A supersonic delta-wing interceptor could work, and that proof opened the door for something far more ambitious. A machine designed not just to fly faster, but to be controlled by something other than the pilot inside it. By the late 1950s, the United States military confronted a truth it could not engineer around. Human operators could not process radar data fast enough. Plotting bomber tracks by hand on plexiglass boards, relaying coordinates by voice-over radio. It was too slow against jet-speed targets crossing hundreds of miles in minutes. The answer was SAGE, the semi-automatic ground environment. 23 direction centers were built across North America. Each one housed an AN/FSQ-7 mainframe computer weighing 250 tons and filling an entire floor of a hardened building. SAGE pulled surveillance data from the distant early warning line and hundreds of radar stations, fused it into a single real-time air picture, and transmitted intercept courses directly into aircraft autopilots through data link. A pilot in an F-106 could take off, fly a complete intercept profile, and fire his weapons, all directed by a computer hundreds of miles away on the ground. It was the first system of its kind anywhere in the world. But SAGE carried a devastating flaw that surfaced during Operation Sky Shield, a series of live exercises simulating massed Soviet bomber attacks. Against coordinated low-altitude penetrations, interception rates collapsed to roughly 25%. The system built to guarantee continental defense could be overwhelmed by the very tactics Soviet bomber crews were already training to execute. And that raised a question no interceptor alone could answer. The Convair F-106. Delta Dart carried a designation no other aircraft received, the Ultimate Interceptor. It earned it. Mach 2.3 in level flight. A world speed record of 1,525.96 miles per hour set in 1959. The Hughes MA-1 fire control system linked directly into SAGE, enabling fully automated intercepts from takeoff through weapons release. The pilot monitored, the system fought. Internal armament it included AIM-4 Falcon missiles and the AIR-2 Genie nuclear rocket. No gun was fitted initially, because a gun implied close-range dogfighting, and the F-106 was never supposed to dogfight. It was a guided missile platform launched on command from the ground. Across the Atlantic, Britain's English Electric Lightning answered the same threat with a radically different philosophy: raw, vertical performance above all else. Twin Rolls-Royce Avon engines, stacked one above the other inside the fuselage, produced a climb rate exceeding 20,000 feet per minute. Nothing in NATO or the Warsaw Pact climbed faster. 30mm Adden cannons and Firestreak infrared missiles provided the killing power for point defense of Royal Air Force V-bomber bases. But the Lightning paid for that extraordinary climb with a combat radius of barely 150 miles. Both aircraft represented the absolute ceiling of the dedicated interceptor concept. Both were remarkable machines built to perform a single mission with total commitment, and both were being made obsolete before they reached peak deployment. The primary threat was shifting from bombers cruising at 60,000 feet to warheads descending on ballistic arcs that no interceptor could reach, no radar could track in time, and no pilot could chase. The Soviet Union built its interceptor force for a fundamentally different landscape. On the PVO Streny, the air defense forces defended millions of square miles of Arctic coastline and Siberian wilderness served by scattered air bases separated by enormous distances. The Tupalev Tu-128 was designed for that emptiness. It remains the heaviest fighter aircraft ever built, 43 tons at maximum weight, carrying 4 R-4 long-range missiles on underwing pylons, capable of loitering for over 3 hours across territory no lighter interceptor could cover. The Sukhoi Su-15 became the PVO's workhorse, with 1,290 produced. Fast, reaching Mach 2.1 and integrated into ground-controlled intercept networks through the Lazur data link system. It became infamous not for any bomber engagement, but for the destruction of Korean Airlines Flight 007 in 1983. The MiG-25 Foxbat was the aircraft that terrified the West, built from welded nickel steel to survive sustained speeds of Mach 2.83, designed to intercept the American B-70 Valkyrie and the SR-71 Blackbird. It was the most feared interceptor of the Cold War until Lieutenant Viktor Belenko defected to Japan in 1976, and Western analysts examined the aircraft firsthand. They found limited low-altitude capability, engines that overheated past Mach 2.83, and a maximum maneuvering tolerance of just 4.5 G. Its successor, the MiG-31, finally introduced look-down, shoot-down capability through a phased-array radar. But by the time it entered service, the question had changed entirely. Both superpowers had spent decades and billions perfecting machines to fight a bomber war that intercontinental ballistic missiles had already rendered secondary. And no American interceptor ever fired on a Soviet bomber. No Soviet interceptor ever engaged an American strike aircraft in anger. The most expensive, most specialized, most technologically extreme combat aircraft of the entire Cold War fulfilled their mission by never performing it. That paradox is the interceptor's true legacy. Strategically, these machines embodied the logic of early nuclear deterrence, the desperate years before mutually assured destruction was fully accepted, when both sides believed bombers might actually penetrate defenses and deliver a decisive first strike. Technologically, SAGE pioneered the networked command and control architecture that evolved directly into modern integrated air defense systems used by every advanced military today. With the data link concepts tested inside F-106 cockpits became foundational to every fighter aircraft built in the decades since. Economically, the programs consumed resources vastly disproportionate to the actual bomber threat, once ballistic missiles dominated strategic planning. But no defense planner could afford to assume bombers were irrelevant until it was conclusively proven. By the mid-1970s, multi-role fighters like the F-15 Eagle replaced dedicated interceptors entirely. The era ended not with a final engagement, but with a quiet institutional acknowledgement that the threat had evolved beyond what any single aircraft could answer. What remained was a generation of machines that proved exactly how far engineering will reach when extinction is the only alternative.